Okay, this is the last lecture from chapter 6. Woohoo! Tearing right through this stuff. All right, so the ionization energy, I already told you, that's the amount of energy it takes to pull an electron off. The actual textbook definition of this is that the ionization energy is the amount of energy required to remove an electron from the ground state of a gaseous ion or atom. All right, so let's click. Come on. Here you go. Right, your first ionization energy is the energy that is required to move the first electron. Second ionization energy, that's the energy required to move the second electron. And third ionization energy is the energy needed to take out the third electron, and so on. So you can ionize something multiple times, right, until you run out of electrons to pull off of there. So my question to you is, before I click over to this next slide, do you think the ionization energy stays the same? So, for example, if it takes 1,000 kilojoules to remove the first electron, does it take the same amount of energy to remove the second electron? Or does it go up? Or does it go down? So, I guess there's three choices there. It stays the same, it goes up, it goes down. So make a prediction. Get it in your brain. Dun-da-da. All right. So the answer is it goes up. All right. So the more electrons you pull off, the harder it gets to take electrons off. Because as soon as you take off one electron, now what you're left with is a positive ion. All right. So you have this positive ion. So that makes it harder to take out the next electron, because the more electrons you take out, the more that positive charge outnumbers the negative charge and just holds onto them tighter and tighter. So when you take these electrons out, as you're pulling them off one by one by one, once you get to the core electrons, it goes crazy. It really does not like to give up the core electrons. So it'll spit off those valence electrons, not happily always, but like you can remove those valence electrons. But once all the valence electrons are gone and you get to core, it just goes crazy. So let's look down here at sulfur really quick. All right, so if I'm looking at sulfur, all right, to take off the first electron, it's 1,000 kilojoules. The next one, 2,200. Next one, 3,300. Next one, it's pretty good pattern here, right? So you have 1,000, 22, 33. This one's about 44. So it's 45, whatever. So we got a good pattern going. Boom, 7,000. This one took a little bit bigger jump, bigger than you'd guess. I mean, there looked like we had a nice steady pattern going on here, and I would have predicted this would be around 55 or 5,600, somewhere there, but it's 7,000, so it's a little bit more. Then about 8,500, and then that's all the valence electrons. So when you want to take a next one out, it's a core, and 27,000. So it goes from 8,500 to 27,000. Huge jump. So what's going on here? So if I actually bring up the diagram of sulfur. So sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. So I just kind of drew it all out there for you. So the orbital diagram, the first electron that's going to go is going to be this guy right here. So get out of there. Boom. That was the 1,000. The next one, boom. That was the 2,200. Boom. This one was the 3,300. Boom. That was the 4,550 something. All right. Do you see now why there's a little bit of a leap, a little bit of a jump? All right. So this next one, boom. That was 7,000. The reason this was more is because these are coming from the 3s orbitals. They're deeper. They're closer to the nucleus. They're harder to get out than the 3p's. So it's coming out of the 3s orbital. So that's that little jump you see. And then bang. So that was all the valence electrons. So the valence electrons are all in this third shell. If I want to take out one of these, the first one to come out of here would be this one, and that's going to be 27,000, and it's huge. So to get rid of those valence electrons, not too much of a problem. But if you want the core electrons, you're going to have to work to get them. All right, let's talk about sizes of ions. So yeah, the size of the ion is going to depend on your nuclear charge, number of electrons, orbitals, all this stuff, blah, blah, blah. Don't worry about that. I'm going to get right to the nitty gritty. All right, cations are always smaller than parent atoms. What the heck is a cation? I kind of just blurted that out. So cation is a positive ion, and anion is a negative ion. So cats have paws. Meow, meow. Get it? Cat paws, positive ion. All right, that'll keep them straight for you. So a cation is always going to be smaller than the parent atom it comes from. So when I take an electron away from a lithium atom, the remaining electrons are pulled in more tightly by that nucleus, so it shrinks. So lithium cation is smaller than lithium atom. Sodium ion is going to be smaller than your sodium atom, and so on. So that is the trend. And when you're going up and down, it's still kind of the same deal, right? So if you're looking at all these different ions, the group 1 ions, they are still small on top, and then get bigger as you go down. As I move across the table, right, you get smaller as you go from left to right. And even with the ions, so lithium plus, beryllium 2 plus, boron 3 plus, they get smaller as you go across. And you might be wondering, like, why are these are all 1 plus and these are 2 plus and these are 3 plus? I'm going to get to that actually in the next chapter. So don't worry about that for now. So if cations are always smaller than the parent atoms, what do you think about anions, negative ions? Boom. If you guessed they're bigger, you guessed correctly. All right, so oxygen atom is here in the gray. Oxide, right? It's O with a 2 minus charge, so bigger. So when you add extra electrons to it, there's more electrons. There's more electron repulsion. The whole thing kind of like swells up. So anions are always bigger than the parent atoms. All right, couple more slides here. There's something called electronegativity, and it's a measure of an atom's ability to attract electrons towards itself. And basically what things are trying to do, the reason they bond, and we're going to get all the like bonding, all the stuff in later chapters, but they're trying to achieve what is called an octet. They want to get a totally filled S and P sublevel. Like if you totally fill up the S and P sublevels, that's 8 electrons. So that's why we call it the octet. So the octet rule is basically saying that things want to be like the noble gases. So all the noble gases, they have an octet. They have a completely filled S and P sublevel. And that's one of the ideas is that that's why they're so stable. That's why they're so unreactive, is they're really happy. And all these other things are trying to be like that. So that's what's going on here. But the most electronegative thing here is going to be fluorine. All right, so this actually follows the same trend as everything we've talked about. All right, so when we go, let's see. Bleh. So if I go down a group, right, it's less. And if I go across the table, it goes more. So ionization energy, it's less when I go down. It's more when I go across. The electron affinity, less when I go down, more when I go across. So all three of those trends, like this and those two trends, they all match up. The one that's these are all related to is actually size. But if you want to think of it, it's almost like they're inversely related to, because the bigger it is, right, the lower the ionization energy. The bigger it is, the lower the electron affinity. The bigger it is, the lower the electronegativity, right? And so easy. So we're going to mainly deal with these guys right up here. We never deal with the D block, so don't worry about electronegativities down there. And we rarely, I don't think I've ever dealt with these even. So hydrogen we'll play with a lot, and usually it's these nonmetals up here that we're going to start dealing with in chapter 8 when we start doing polar covalent bonds, and we're going to talk about how they share electrons but not evenly. So it turns out like fluorine, it doesn't share very well. It's the worst sharing one of them all. It has the highest value of electronegativity. Oxygen's number 2, and then nitrogen and chlorine are tied for 3rd, but these are the most electronegative elements there are. That means they really like electrons. And you might notice that like over here, the electronegativity is 0. That's true. All right, neon's got the perfect number of electrons. It has no desire whatsoever to increase the number of electrons. Like it already has the perfect number. If it added electrons to it, that would make it worse. So these have no electronegativity at all. All right, they're noble gases. They're already, that's what everything else is trying to be like, is these ones. So that's makes sense. All right, that's this chapter. So we will head on into ionic bonding, metallic bonding, and stuff in the next chapter. I will see you there. All right. See ya.